And all right, so this is math reasoning, which is one of my favorite classes to teach, and I haven't gotten to teach it. I haven't taught it in like 5 years actually, so I'm pretty psyched right now. Pretty psyched also because, well, it's fun to see you all, and I know some of you already, and the rest I'll get to know. But let me go ahead and start sharing screen. So I did make the Blackboard available early this morning. Oh, by the way, just so my audio is, I should have done this before I started recording, but in my class yesterday, I had the wrong audio thing and people were trying to talk and I wasn't hearing anything. So some people could just say hi to make sure I can hear you in my, uh-oh, I don't hear anyone.
Hi.
Oh, okay. Nobody wanted to say hi. Okay. Okay, good. Now I hear. Okay, so yes. All right, so this is our Blackboard. This is what you should see. I'm in the student preview mode. I don't like Blackboard, so I have everything. It's just this link right here. So you can always find this link at Blackboard, or you can save this, for yourself. And so here is our class. Maybe I can make this a little bigger. All right, so math reasoning, I'll come back to these pages, but let's just go through some of the logistic stuff and then we'll get into actual, like, what is mathematical reasoning? So that's me. I've been here for a million years. My office, once we're back, I'm in my office right now, once we're back on campus back together next week, you'll see I'm just at the end of the hall. And then this is a Zoom link, which you must already have. I have a bunch of office hours. Like, I guess I teach 9 to 10 a.m. Monday, Wednesday, Friday, so I have an office hour right after that, and I teach like 10 a.m. to 1 p.m. on Tuesday, Thursday, back to back. At least one of you gets to be is in both of those classes. Gets to sit with me for 3 hours. But so then later in the afternoon, Tuesday, Thursday, I have office hours, and then some other office hours. I do. One thing I got a few students mentioned last semester, which on the course evaluations, which made me a little salty, was that people were like, oh, he's always like canceling or changing office hours. And I was like, well, I have a lot of them. So like, yes, sometimes like something comes up where I have a conflict and I have to like reschedule or cancel one. So, but I have a lot of availability, and like, I can also meet people by appointment or other times. So I'm very available, and I really like talking to students and, talking especially like one-on-one or in small groups. And so, so please, like, especially if like for some reason you're just not having fun in the class, you should definitely come talk to me. But also just like, I would just recommend dropping in periodically throughout the semester, just to say hi. We'd have a study group I'll talk about down there a little bit. We have this Gather classroom, which is this 2D environment. I'll show you this a little later. We might actually use this on Thursday, at least for group work, and this week for office hours, because we're remote. But it's kind of fun. I'll show that to you. Okay, and so we meet. Then I think it's 10:05 to 11:30. Hopefully you have that right. Yeah, and then right. So Gabriel Ong, who's a great math major junior, I think he's a junior. I put 23 without checking, but he'll have a study group once a week, which is just another place you can go hang out and talk to someone who knows their stuff and can help. So yeah. So I'm still setting that up, so we'll have to decide when that is. This is the textbook. It's actually the library has it as a digital resource, so you can actually download the PDF, or I just actually put a link to it right here. If I think I can show you the textbook. Yes. All right, so yeah, this is a textbook. I mean, it looks like, the cover looks like that. Introduction to Mathematical Structures and Proof. You guys can see this share, right? Just some thumbs up or good. All right, I'm always worried about the technology. So where did the contents go? Okay, there they are. So yeah, so we're gonna go. This is a great book, and it's the whole point of this class is to start talking about, mathematical language, what proofs are, how to be really rigorous, how to write things all down in a very clean way, a lot of the terminology, notation, and just like the methods of how you actually write rigorous mathematical arguments. And so there's sort of some natural things, like we need to talk a little bit about sort of just logic, like propositional logic, although that's more in the background, but you still have to sort of know the basics of that. When it's not like there's a logic class in the philosophy department that really goes deeply into that stuff, and we're not, I think mathematicians are like very adamant that they're not logicians usually, like we're not diving deep into like, you know, super duper low level stuff. And I'll talk very soon after we go through the logistics about like axioms and proving things from axioms. So we'll dive into this logic pretty quickly, and then sets. Everything in math is in the language of sets. So we'll go through all the set notation and logic and arguments and properties and all that stuff. And also like maps between sets, which is what a function is. Like you've seen functions from the real numbers to the real numbers, like squaring, like y equals x squared, right? Like you input a real number and you get out a real number. But you can sort of talk about maps from any set to another set. And so we'll way generalize all that stuff you did in high school, and talk about sort of general, but like you can really think everything in math can be expressed as a set or a map between sets. And so we'll be doing, this is a very fun part of the course. We'll definitely also talk about cardinality. One of the things that's like fun in this class is proving that the real numbers are uncountable. There's like a famous argument there. It's another thing that's fun about this class. I get to show you some of the like most famous arguments in the history of math, which is just, and they're cool. So it's like a culture thing, almost like, you know, good stuff for cocktail parties, like, you know, talking to people about, people love math. Oh my God. We'll maybe touch a little bit on the combinatoric stuff. I'm a number theorist and I really like all this stuff. And in fact, this will kind of be in the background. We're actually going to do a little bit today, because I think that's a great way to start from some axioms and start proving some stuff is, you know, like we can actually build up to the proof of the fundamental theorem of arithmetic, which is a fancy name for just saying that every number has unique prime factorization. But we're actually going to prove that in this class and see how you can build up from axioms all the way to proving that. So this stuff will be in the background. I'll sort of pepper it in here and there probably, especially when it illustrates earlier concepts. And then complex numbers are also great. I try to fit those in at the end of this semester. So yeah, so that's kind of a little bit of an overview. So just if you're sort of thinking about what to note to yourself, maybe just, we're going to cover the first 4 chapters kind of straight through with parts of chapter 6 thrown in, and then when I can, parts of chapters 5 or so. So, okay, let me go back to the web page. Where did you go? Yeah. Okay, so that's the textbook, and so at least a little brief glimpse of what we're going to be doing. And then we're going to use this grade scope. I still need to set it up, so I'll set it up by Thursday, and I'll probably show it to you in class Thursday. But I really like this. You can sort of like, actually, you're going to be typing your homework because we're going to be using LaTeX. Maybe not for everything, but for at least any proofs. And I'll be talking about that, which is like the math typesetting language. And so, in fact, I guess I just copy this from another class, but you probably won't even have to scan. You can just you'll just have a PDF file you can upload. And so we'll have a problem set every week. I know you guys have different problem sets different times a week. So I just decided threw it in Tuesdays by 11. Although what I usually do, especially on Gradescope, is I usually give a grace period of like 48 to 72 hours for students to turn stuff in. I'd like you to stay on the schedule with the rest of the class, but like if there's some weeks where you just can't get it done by Tuesday, you can turn it in, no harm, no foul, over the next couple of days. So that's another reason I put it on Tuesday, because often the graders want to grade over the weekend. And so if I had it Friday, but then certain students weren't turning it in until Monday, then the graders get annoyed at me. So, so that's it. So I think that's a good timing. And I'll try to see if I can get Gabriel to schedule his study group, like maybe Monday night or Sunday night or something. And then I would like to offload some stuff to video notes where I ask you to take notes. I have a few things on video, and it's a question of how much time I'll have to make videos. But if I'm going to just be like lecturing at your faces, then I feel like I might as well make a video and have you just take notes on it, and then we can sort of discuss it together. And then we have more time when we're actually together to like, you know, go more deeply into subtleties and discuss things and do more group work and do more. And even if we, you know, if I give you a lot of videos to watch, I'll definitely try to like schedule some time during the class to like spend some time on, like you can spend some time on the problem sets, just to give you like, so that I'm not like overloading you with stuff. Does that make sense? By the way, any questions or anything, please ask. Actually, I'm not, where did the chat window go? Oh, I'm sharing screen. Okay, I have the chat window there. So please feel free to put something in the chat or just speak up if you have a question. And then for the grading, I mean, I just have it set up as like homework, midterms, and final, each 25%. I've really gotten into the habit of like, I just want everyone to do well. I used to give, you know, sit down exams where I would like take points off and everybody's looking at the curve and trying to figure out. And I'm just, I don't know, maybe I've been teaching too long. I'm just tired of it. And then students are all, you know, anxious and stressed out. And it seems to increase every year. And the pandemic certainly hasn't helped, right? And so I'm just trying to make it so everyone, like, if you put in work, you'll get a good grade and not worry about it. And then you can focus on the learning. So for example, I've started making exams like all take home and all and like open pretty much, where you can like talk to whoever you want. I mean, you can like talk to each other about the problems. I have some caveats, and I'm trying to write this up right now, so I'm gonna like post, like I think at the top of this page I have a grading exam information coming soon. So like I'll talk about this more, but what I'm sort of thinking right now is that you can talk to each other, but you can't write anything down with each other. Like you can't write down and show people stuff. Like, so I'll let you, like, you can look at the textbook, you look at your notes, you can talk to people, you can look online, whatever, you know, but I just don't want you, like, my idea is that like, if you talk to each other, it's like, you're not just like copying down what the other person's saying or like what each other's saying or writing the exact same answer. I really think a lot of this course is the writing and learning how to write and almost like have your own style of mathematical writing, because it really is like something a skill you develop, and everyone kind of has their own style. And so the thing that's really important to me is that you sort of write your own answers. I mean, for lots of reasons, for academic honesty reasons, but also just for like, the writing is what you want to really do on your own. So, so I think that's going to be the caveat, is that like everything's open, but if you talk to other people, like in the class, you can't like talk and write. You can talk, but you can't like write while you're talking, if you know what I mean. Hopefully that makes some sense, but feel free. I mean, especially once I post more explicit instructions, feel free to like pick me apart on that and see how that could go wrong or right. But does that seem reasonable? All right. And even after you turn in the exams, if like you got a low score on a certain problem, I'll definitely give you a chance to rewrite for like almost all the credit back. So a lot of it's just effort. If you sit there, because like I've been doing this with my classes actually, and like even like in like integral calculus, whatever, like my students were writing like these beautiful solutions to these problems and showing me they really understood stuff. And so I'm giving a lot of good grades. I mean, I'm giving a lot of A's and A-minuses now, and it's like, it's fine with me. I don't know if the administration would be upset, but it seems like students are learning a lot and getting out of it. So like, I'm happy to just give good grades. So that's kind of my whole approach. Okay, and then yeah, all the sort of typical pandemic stuff that like, don't come to class if you're feeling anything. I've gotten in the habit of recording, and like I said, in the classroom, I have like a mic pack that I can like strap and like record the Zoom. And it also doesn't really pick up student voices, which again, if you don't want to be on recordings, you don't have to be. But I do try to remember to repeat the question so that it's actually picked up. So I'll be like streaming the class over Zoom and probably recording. So like, if you're sick, just don't worry about coming to class that day. I won't stream or record group work. Group work is like its own thing. Well, maybe we'll be streaming, because if there's students remote, then they want to do group work also, but I won't record that part of the class. And then about group work, like, it's not really a thing this week, but starting next week, like, it didn't come up last semester, but you know, if you really don't want to be that close to other people, like because you're working at the boards and stuff, then it's totally fine. Like your safety and your comfort is the most important thing. We can figure something out, but just be, you know, straight with me about how you feel. Like if you're feeling uncomfortable at all with any of the setup, let me know and we'll accommodate you. So cool. So that's any questions about any of this so far? Feel free to, like I said, drop a thing in the chat or just pipe up. It's all pretty straightforward, I think. This is the main page that I'm sort of starting to set up, which is like, and I've almost got the problem set ready to post for next week. That'll be the first problem set. And I will post, I mean, I'll try to start posting outlines in advance, but like, for example, here is like, I sort of wrote out just like a little like outline of what I plan to do. So, I mean, sometimes it might not really show up till the morning of class or something, but I'll always try to be posting stuff. Or at least maybe brief outlines and then fill them in. And then after class, I'll post the recording here. I might, you know, change this based on what actually happened in class, like if we didn't cover everything, or maybe a little flesh out a little bit. So I'll always try to, I think I've sort of started doing this now, and it's a nice setup where it's like, we're just kind of keeping track of everything. And in fact, I don't know, I'm using this thing called Notion, and it's got this whole database thing where it's like, I can put like a date and a tag and, you know, topics and stuff. And then for the problem sets, there will also be like, you know, a deadline on it and all this stuff. So I made a few notes down here, like, yeah, I need to talk about LaTeX, but I somehow didn't think about it till like yesterday. But I have tons of stuff I've written, and the problem set, like I said, LaTeX is this typesetting language, and there's ways to do it in the cloud now. There's this thing called Overleaf you can use. In fact, yeah, so you can actually like type over here, and then it renders the PDF over here. So it's like how all the beautiful math is made. I'd have to find my Overleaf account. I use, since I'm an old person, and before all this was a possibility, I have my own like local thing on my own computer. And you can download programs and do LaTeX on your own computer also, but a lot of people like this cloud version. So I'll show you some of this, and then I actually comment on a lot of the code to tell you how things work. So I think Thursday I'll show you some of that. And I'll post the first problem set today, so you'll be able to see that also if you open it. Because the source you can just open in any text editor, and then it renders, once you run the typesetting, it renders a PDF. And then it is in the cloud, but you'll be able to download this and like submit it. I might even have you submit your text source also, because then I can steal shamelessly from you. And I mean, I'll be giving you all this text source for the problem sets, and you can actually use the problem set to just type your answers in between, you know, and then, you know, once you type stuff up, then I can steal it. It's always about stealing code from everyone. That's kind of a good skill. Okay, so we'll do more LaTeX on Thursday, since I didn't think about it in time. And then I'll have the grade scope set up on Thursday, so I'll show you that too. So some of this is even just like notes to myself, like, and I'll try to put announcements and stuff too, just to remind myself, like, I'll just try to have everything organized here. Okay, any logistical questions before we move on to actual math? Super excited to do math. I know I am. I mean, this course is it's a fun course. It's like, it's different. It's any different from calculus or even linear algebra. It's definitely about sort of moving into like the real nitty gritty of like logic and rigor. And it takes a while to learn how to write a proof. Like, it's not the most natural thing. And I'm going to show you, like I said, I'm going to show you a nice formal proof. And I'll start writing. I'm going to switch to the iPad and start writing on the iPad. So let me do that. Yes. Okay. So So let's see. I wish my handwriting was like Professor Tabak's handwriting is like incredible. Like I especially on iPad, I still don't love the feel of like the plastic on glass. Although I have some masking tape over the tip of my iPad pencil, but but actually I'm just realizing it's worn away. I need to replace it. Anyways, so my handwriting is not going to be super fantastic, but tell me if it's unreadable. So so the idea, I guess the statement, I should say, maybe we'd call this like a proposition or a theorem or something. We'll talk about what all these words mean. Like there's like lemma, corollary, theorem, proof, proposition. We'll talk about all these words. So given any integer a, you all know that a times 0 equals 0, right? That's just something that you know deep in your bones. And so the question is like, how would you prove this? And I guess I haven't actually checked in with students with this, but you still do like that sort of like high school geometry proofs. Most of you see nodding, at least from the students that I can see right now. Yeah, so like there is something where there, and it's a general thing, which is like you need some axioms, you need somewhere to build on to be able to prove something, because you're trying to do like logic. It's all deductive. I mean, I guess that's a big thing in math, is like it's all deductive logic. Like we're trying to start from some first principles and like just use rigorous logical steps to derive other truths, right? As opposed to inductive logic is like the sun has been rising every day, so I believe it's going to rise tomorrow, and that's like an inductive reasoning sort of thing. So inductive versus deductive logic we'll talk about, but so we need some axioms first about the integers and how they work. And this is all going to be very familiar to you. It's just maybe, I don't know if you've like codified it in quite this way before. So the first thing I'll say is like the integers. Oh, that's not the color I wanted. That's a little oranger than, oh, no, that's good. The integers. So it's a set, right? It's denoted, the way that mathematicians write it, and you may have seen this some, but now you know, it's denoted like this, Z. This is called a Blackboard bold Z, like where you have like the double bar on the Z on that. So it's just like, there's a terminology for this, which is Blackboard bold. So a lot of sets are written with these languages. Does anybody know why it's called Z? Any German speakers? Does anybody know the German word for integer or number? No German speakers, huh? I'll see in the chat either. It's Zahlen. So it comes from the German word for integers, or numbers. I'm not sure exactly how it translates, but it's denoted Z. We also have like the real numbers are written as R. Oh my God, handwriting is so bad. Real numbers. Like R, like that. The rationals, the fractions, are written as a Q for quotient. So we'll see, like there's just different, there's these, but again, they all have this sort of like Blackboard bold of this like double barred thing. It's just a very standard like mathematical notation. In fact, I don't even like, let me try to write that better like that. Okay. Okay, so it's a set denoted Z, and it has two so it's a set, meaning, because you're used to it, it's a collection of, what's a set? It's just a collection of things, right? So it's a collection of numbers. It's a very nice collection in that it's like, you know, you can like list them all very nicely, and we'll talk about that later in the semester. And it has two operations, right? Set with two operations, which are addition and multiplication. plus and times satisfying the following axioms. Okay, so let's talk about some of the basic axioms that we use. Not sure why I went full orange there for that whole thing, but back to white. So there's some sort of like classic ones, right? So there's like, and these are operations about, I mean, these are axioms about the operations and how they work. So what do you know about addition or multiplication? Can anybody guess what some of the like laws or axioms like that we're going to use are? Have people, you know, there's some words, fancy sounding words. Does anybody know what I'm getting at? No. Okay, I appreciate that. Sometimes I ask vague questions that are not well formed, and I'm just like seeing if somebody can divine what's in my head. Well, so when you add, does the order matter? No, and what's that called? Does anybody remember what that's called? It has a fancy name.
The commutative property of addition.
It's commutativity, that's right. So in fact, addition and multiplication are both commutative. In fact, maybe I think those are, do I want to call that one axiom or two? No, it's just one. Okay. So i.e., so to make that a little bit formal, we would say, given any, for any, so here's already a notational thing, is we write something like this. And this means A and B live inside Z. Just means those are, this is this little, in fact, maybe I should have really focused on this, is really the live inside. It's like is an element of, sometimes used, it's like this little epsilon looking thing. So for any A and B and Z, we have A plus B equals B plus A, and A times B equals B times A. And I'll just use a little dot for multiplication, or even sometimes we just won't write anything, right? We just use juxtaposition, like AB equals BA. We could write, I'm not going to write like the multiplication sign, but AB equals BA. Right, so that's one of the properties we have. So commutativity. Is there another one that you've heard of that's like commutativity, but something else?
I was going to say associativity, but I don't know if that.
That's right, associativity, associative, yeah. So it's a different sense in which addition and multiplication, the order doesn't matter, but in a sort of slightly different sense, right? Multiplication are associative. So that we would say for any A, B, and C. When I say for any, we'll talk about this, it's called the universal quantifier, but like, it's like for any choice, we could choose any two elements out of the integers to do A plus B equals B plus A. Now we're going to choose any three elements out of the integers for any A, B, and C in Z. We have, so it's that thing of like, it doesn't matter if you add the second and third together and then the first, or add the first and second and then the third, right? And then something similar for multiplication. A times BC equals AB times C. So associative. Commutative and associative. There's one more word like that. Fancy sounding word.
Distributivity.
That's right. The distributive law. So the fact that, so the way we would say this is multiplication distributes over addition. Over addition. So now this is again for any A, B, and C. Or you can also write for all A, B, C. And there's also a symbol. There's going to be a symbol we're going to use for this. That's an upside down A. If you've ever seen an upside down A in some like weird logic book or something, that's what that is. It's just a way to say. Mathematicians get really lazy and like to start writing things like as quickly as they can. So they came up with this upside down A just to like not have to write out for all or for any. I actually try to like write stuff out and not use all the symbols all the time because it reduces readability. And especially when you're typing, it's really just as easy to type for any than to actually like type the little command that makes this upside down A symbol. So for any A, B, and C in the integers, if we do A times B plus C, that's the same thing as A times B plus A times C, right? Okay, so those are three fundamental, just like laws. Let me give you two more that, actually, sorry, three more. There's a special, one thing, like if we're trying to sort of axiomatically define the integers, we have to sort of say some specific integers because some integers are built out of all the rest, right? I'm sorry, so most integers are built out of just a few. I said exactly the opposite of what I meant to say. So there's a special integer called 0. So addition has an additive identity is what it's called. So this is the fancy terminology. You may have seen this too. Maybe some of you wanted to say it and I didn't give you the chance, so I apologize. So addition has an additive identity. There is an element, or there's just an integer. I was going to say an element of the integers, but why don't I just say there's an integer. Denoted 0 such that A plus 0 equals A, and I might as well just put equals 0 plus A. It doesn't really matter. I mean, you could use the commutative law to justify that, but sometimes it's nice to put this for any A, for any choice of A, right? A plus 0 equals A. So that's an additive identity. So it's like, that's just the word identity means like doesn't change something. So this is the integer that we add that doesn't change anything, right? So addition has an additive identity. Hasn't, I don't know why I said additive. It's kind of redundant actually. Addition has an identity. Similarly, multiplication has an identity. So what's that special integer called?
One.
There you go. It always seems almost silly to go through all this stuff because it's like, this is all the really obvious stuff, but you have to write it down once and make it all really sort of like abstractified. So I'm just trying to make this look as much like the previous one as possible. So A times 1 equals A, which is also 1 times A for any choice of A. right? So that's the additive identity. And there's one more. If we're talking about integers, there's one more. Actually, sorry, well, actually for any number system. These actually all apply to any number system. So I'm going to say there's actually a name for all these axioms. I mean, they don't apply to any number system. There are number systems that are not commutative, like matrix multiplication is not commutative. So if you're talking about sets of matrices, you can't do that. But most of the number systems we're used to satisfy these properties. Like I'm talking about the integers now, but I could be talking about the rational numbers or the real numbers, right? So addition has inverses. So given any a, in the integers, there is an integer denoted negative. Well, actually, I'll even write it a little bit differently. Well, I don't know. I'll just say it this way. There's an integer denoted negative a. That satisfies, or such that's a term we use in math a lot too. Like there's just start to notice little patterns, like such that is used a lot. There exists or there is a lot. For all, for any, given any, that's used a lot. And here it's such that basically when we add these two together, we get back to 0. Again, for some reason, the way these are usually stated, it's sort of stated both ways. It's actually, I mean, again, it's commutative, so it doesn't matter, but there are, like in matrix multiplication, for example, there are sometimes left-sided inverses and right-sided inverses without there being, like for non-square matrices. Like non-square matrices can sometimes have a left inverse or a right inverse, but not a both-sided inverse. So we usually, when these axioms are stated, they kind of state them both ways to sort of say it's a two-sided inverse. But again, here, since addition is commutative, it's clear, right, that it's a two-sided inverse. Okay, so in fact, lots of sets satisfy these. Not just the integers. In fact, this doesn't determine the integers. There's a few more axioms that we need to like say this is the integers, because lots of different sets satisfy these axioms 1 through 6. For example, the integers, the rationals, the real numbers, the complex numbers. I guess that's what C represents. And there's these finite sets called like modular rings we're going to talk about that are satisfy these also, and others. So the thing you have with like the rationals or the reals is you also have multiplicative inverses, right? That's one difference between the integers and like the rationals or reals, is that you have multiplicative inverses in those sets for non-zero elements. You have to say for every non-zero element, it has an inverse, multiplicative inverse. But that's not true for the integers, right? If we want to stay inside the integers, I mean, 2 has a multiplicative inverse, but it's 1/2, and 1/2 is not an integer. So those are the kind of things we're going to be dealing with. Anything satisfying these is actually, there's actually a name for this. I might as well just tell you. I don't want to completely overwhelm you with terminology. I could just be throwing words at you. But anything, any set, maybe I should say any set with 2 operations satisfying these it has a name. It's called a ring. So sometimes these are called the ring axioms. There's even a course, Math 2702, is called Rings and Fields, which is rings. This is what rings are. Fields, actually, if you throw in the multiplicative inverse axiom, you get what's called a field. So all of these are rings. Like all of these examples, all these examples right here are rings. These are actually fields, called fields, because they have multiplicative inverses. Not so important, but it's just like, you start, I think it's good to just get the terminology out there so you start hearing it so that it becomes demystified, you know? So if you see that there's an upper level course called rings and fields, all of a sudden it doesn't sound as like, in fact, maybe I just took some of the fun, like the mystery out of it, because like rings and fields sound like interesting objects, like geometric objects, and all I'm saying is it's just a name for this number system. So maybe I took all the romanticism out of the, I'm gonna take a class called rings and fields. Okay, again, questions. Any questions about any of these so far? Okay.
Could you actually repeat the difference between a field and a ring?
Oh yeah, let me go and write that down too. I sort of was just saying it, but if we add a multiplicative inverse axiom, so where you're required to have multiplicative inverses, so rather than write that down, I'm just going to say you can imagine what that would look like. It would look very similar to this, but with multiplication, and you'd have to specify that a is not 0, right? Axiom, we get a field. So for example, Q and R, the rationals and the reals are fields, but the integers are not. Right, that's not a field. Because again, it's like, one thing I should say is like, you have to stay within the set. So doing this inverse is like, you don't stay in the set. You can take inverses of integers, but you're not in the set anymore. Good, thank you. Thank you for asking. Cool, anything else? Okay, so now we can do our first proof. So again, proposition. Now I can write it a little bit more. Oops, I wrote the upside down A. For all A in Z, A times 0 equals 0. Because notice that's not axiomatic, right? That's not. I mean, that's the thing. I'm going to actually give you a formal proof, and it's going to look kind of unmotivated. I think it'll hopefully be beautiful and obviously correct. Like it'll follow very deductively just from the axioms. But at some point I want to circle back and try to like ask, well, how does this, how would someone come up with this? And I will say, like, the reason you might even be surprised by this is the only thing we know about 0 is that it has something to do with addition. But now we're trying to multiply it. So we're saying something about the multiplicative property of 0, even though axiomatically 0 is only defined in terms of addition. So, and it turns out that you can use so here's a nice proof. But again, it's not something I would expect you to come up with on your own in day one, because it's like there's a distillation process and a whole thing of like trying to figure out how do you prove something. But I just want to show you like a nice proof. Okay, so here's what we can start with. I want to start with something true, right? So here's something true. The only two integers we really know about at this point are 0 and 1. That's another thing. If you think about axiomatically, the only two integers defined are 0 and 1. In fact, what is 2? 2 is a definition. It's defined as 1 plus 1. And 3 is defined as 1 plus 1 plus 1, right? And I guess we get -1 from the additive inverse axiom. If we have 1, we get -1, and then we can define -2. So like, you have to think about this fact that it's like right now the integers just looks like 0 and 1, and then other stuff. So I want to start with something that's true. And I'm going to just use 0 and 1. So we know 1 plus 0 equals 1. Okay. That's hard to argue with. I mean, you can sort of quote the additive identity axiom, right? From the additive identity axiom. And now I want to introduce this A. So let's multiply both sides. We know we're going to have to multiply, right? So let's multiply both sides by A. We get A times 1 plus 0 equals A times 1. And once you do this, you might be able to see where it's going, right? I mean, that's kind of, it's kind of amazing that I can just tell you these two things. I mean, as soon as you start to simplify the algebra, right, what are you going to get? You're going to get, you can just do that in your head, right? You're going to get, once you simplify the algebra, you're going to get A times 0 equals 0. But we have to actually do that and justify the steps. So, so we'd have to do, I mean, what's the first step we're going to use? What's the first axiom we're going to use to start simplifying this?
The distributivity.
Yeah, we'll use the distributivity. So by the distributive law, I could just say by axiom, whatever number it is, but I really think, especially like I said, if you're typing this out, it's nice to just write out 8, A times 1 plus A times 0 equals A times 1. What's the next step to simplify this? I mean, we have A times 1, right? So we might as well just write that as A. You don't really have to do that step if you don't want to, but the multiplicative identity. Notice I'm starting to abbreviate things like almost immediately because it starts to be annoying to write. We have A plus A times 0 equals A, right? And now, you know, if we're going to do this axiomatically, we actually have to like do more to cancel A from both sides. And so the way to do that is to add negative A to both sides. And already there's an issue here because if I add the negative A's over here on this side, on the right, then I have to like move the negative A through to get it grouped with the A to be able to cancel them out, you know, to collapse A plus negative A. So I'm going to have to use like associativity and commutativity to move things around. So I'm going to add negative A like to the left of both sides. So negative A plus A times 0 equals negative A plus A. Right, so I'm being careful, like if I write more than two things added together, I need parentheses because we don't, you know, by the way, I will say once we get past some of this, we're going to drop that. I'm not going to make you use the associative law like the whole semester, right? Like I'm going to make you use the associative law the first week and then we'll never use it. We'll just use it without, we'll just do manipulations without appealing to the associative law after that, right? So don't worry that I'm going to make you do this like all semester, but I'm just trying to be as rigorous as possible here. Okay, so the associative law is the sort of clear next step, right? By the associative law of addition, I guess, but that's fine. So again, be careful how you write things, but we're going to just move the parentheses. We can sort of shift the parentheses from around the second and third to around the first and second. And we still get negative A plus A. I usually put negative A in parentheses. Did I do that in the axiom? Yeah, I did that in the axiom up here. Just because, I don't know, it can get a little bit dicey if you don't. A plus minus A looks kind of weird. Oh, and did I write it on both sides? Oh, and also notice I did write it on both sides here, which is nice because we don't have to if the axiom only said this, then you might think, well, I have to do a commutative first to put the A first. Again, that's another reason to write just both ways in the axioms. You don't have to do those extra steps. So we know now that these collapse to 0, right? So by additive inverses, we get 0 plus A times 0 equals 0. And we're almost, we're done, basically. We just need one more step, right? Which is we need to make this first 0 go away. So I know for some reason I changed from commas to colons at some point. By the way, these should be sentences. Like, that's another thing that it's gonna be a theme of the semester, but like math is sentences. Like this is a sentence right here. You get this clause. I don't remember what this kind of clause is called, but then this is like noun, verb, noun. That's a noun. Is a verb. Equals is a verb. That's a noun. And so there should be a period. So I sort of believe in punctuating your mathematics. So I've trained myself pretty well to do that. So you'll probably see me do that, but you can try to catch me if I don't. Okay, and then by the additive identity, we can make that 0 go away and then just say A times 0 equals 0. Even that, you could argue, there's different levels of rigor. And you want to find a level that sort of works for you. There's people who get really into the rigor and they would almost argue that this needs 2 steps. And I haven't even said anything about like, well, let me just write this down here. So you could say 0 plus A times 0 equals A times 0. Or actually the other way around even. A times 0 equals 0 plus A times 0. And then we have this 0 plus A times 0 equals 0. And there's this thing called the transitive law of equality that like, if A equals B and B, if X equals Y and Y equals Z, then X equals Z. So then that would imply A times 0 equals 0. But again, this is sort of to your taste. I really believe this class is about fashioning your mathematical taste and like what works for you and what doesn't. Stuff like transitive, stuff like properties of equality, like the fact that equality is like transitive, we sort of use those without saying. So the fact that I just replaced, right, like here, I just replaced 0 plus A times 0 with A times 0. It's actually what I was doing the whole way, right? This replacing with this. Replacing negative A plus A with 0, replacing negative A plus A with 0. And some people who want to be super pedantic would argue that's a 2-step process because you have to actually, state the equality between like these 2 left-hand sides and then use the transitive law to like get to that. For me, that's a bridge too far. It's like, what are we doing here? You may already be saying, what are we doing here with this proof? But like, but you can at least see like we just use the axioms and we got a proof, right? So this is, I'm going to call this too pedantic. Too pedantic. So too much. So we're okay. And by the way, so this is the end of proof. So we're done. And so there's different things you can write when you're done. You can write QED. QED is a famous thing. But I think mathematicians, for some reason, have settled on writing this little square box. So this is like a end of proof done. End of proof symbol. A little box. So it's like, okay, we're done. We did it, right? So that is a proof. Feel good about that? Is there any part of that that's assailable? You're trying to come up with an unassailable argument, right? Is there anything there that's, maybe there is. Is there any step of this that's sort of like, We use the axioms. We know 1 and 0 exist. Again, there's also to taste. There's some people who would want to say even a statement before this, which is like, there exists 1 and there exists 0, just to like create those. So you're not just like using them. But I mean, they're stated in the axioms, so I think we know they exist. So I don't tend to do that. And again, another step, some people would say you would need a step saying in between here saying that there exists negative A by the additive inverse axiom. But so it's like rigor. I mean, again, it's a balance. It's a balance. It's like rigor, but also readable. There's a statement I've heard, which I really like. Of course, I like it because I'm a mathematician, which is like mathematics is the art of explanation, which I think probably most of my colleagues in other disciplines would take exception with, that we have a monopoly on that, because that's kind of what everybody's doing in academia. But there's an aesthetic sense of like writing something that's readable, but yet rigorous. And I think this is a nice proof. Again, anybody have any issues with anything or want to discussing the steps, or is it just all totally transparent? The thing that is not transparent is, how did I come up with this? I didn't come up with it, by the way, obviously. But how did people come up with this? It's because this is definitely unassailable. We definitely start with something that's true and then build. And I do think that there's something about seeing proofs coming out of nowhere and in fact, when you read math textbooks, a lot of it is just like, here's a theorem, here's the proof. And the proof is not motivated. And they just tell you, and it's sort of like, okay, but how was I supposed to figure that out on my own? And then that's a bad feeling, right? And the reason that people have done this is because they've spent hours or centuries thinking about these things and distilled all the stuff down to like this very small, this very elegant, perfect small argument. But even here, like I wouldn't expect you to just come up with this off the top of your head. And so part of what I'm talking about is like what different proofs could look like, and messier proofs. And also part of what I want to talk about is like what the motive, like why, like this doesn't really tell us like why a times 0 equals 0. Like, do you feel like now, like, could you explain to a 5-year-old why a times 0 equals 0? Maybe 5's too young, I don't know. Well, my niece is 4. She could probably handle it. She's into math, which is good. But yeah, like, because there's something about proof versus like a convincing explanation. This is a formal proof, but I don't know that it's convincing in terms of like, now I feel in my bones why a times 0 is 0. You know what I mean? I guess that's my question. And that's really one of the themes I wanted to bring up early in this class, which is, do you feel this is a nice formal proof? But do you feel in your bones? This is a way when I was sort of learning how to write proofs, this is like one of the things we would talk about, like, do you feel in your bones why it's true? That a times 0 equals 0. I mean, you certainly feel that it is true because you have at least 18 years of experience. Well, maybe not with a times 0 equals 0, but like you've got at least like 10 or more years of experience with like knowing that when you multiply something by 0, you get 0. But so that's the first thing I would say is like, do we have a sense of why it has to happen? And again, this is stuff that you could spend weeks and months and years thinking about. I mean, I think honestly, this is one of the first proofs I learned, but I think in some ways, I don't think I understood it for years until I sort of had some insights. Like I didn't feel in my bones for years, even taking math classes and stuff. And so now I feel bad because I'm gonna shortcut you my feeling of like why it's true without giving you the years to mull it over. I apologize. You can, it's like a podcast when they're going to spoil something and they say like fast forward 30 seconds. No, just skip the spoiler or come back after you've seen the movie. Yeah, so, you know, the first thing I would say is it's something kind of what I said early on, which is like why a times 0 equals 0 isn't axiomatic. Well, certainly this is why it's not axiomatic, because we can prove it. But from the other axioms, so like, you know, since we can prove it from the other axioms, let's not make it axiomatic. But also, like I was saying, 0 is this additive thing. It's a special additive thing. A times 0 equals 0, right? But we're using multiplicative properties about it. We're trying to prove a multiplicative property, I mean. There's only one axiom that connects multiplication and addition. Which axiom connects multiplication and addition?
The distributive law.
The distributive law, that's the one that connects multiplication and addition. And so, yeah, this one. In fact, this is the only thing that says how addition and multiplication are related. But like, you know how, again, in your bones, you know how addition and multiplication are related. When you learn what multiplication is, what is multiplication? Like, what's the phrase in terms of addition?
Repeated addition.
It's repeated addition, right? Exactly. So multiplication is repeated addition. In fact, the distributive law sort of captures that, I think. Like, you know, like think about, well, maybe I'll write it down here. So I'll say this is a multiplicative property. I mean, even this is too high level. This is not like the explaining to a 5-year-old level of this. This is still like a high level. Have you seen those? I've seen some YouTube videos online now where like you have an expert explain something at like 5 different levels, to like a child, to like a high schooler, to like a college student, to a PhD, and to like an expert, or like a grad student and an expert. It's the same kind of thing. It's like you want to think about the different levels on here. So it's a multiplicative property about 0, which is an additive concept. So in fact, we have to use, I think, I guess I would claim that this proof better have the distributive property in somewhere, because how else are you going to connect multiplication to addition? But the distributive law is the only axiom of the one, you know, that we listed, connecting. I'm going to start writing plus and times. So it better be in the proof. That's the first sort of like thing I want to say. Okay, so that's the first I want to say. This, and really, you know, multiplication is repeated addition. I claim that is what's inside the distributive law is really saying. Like, for example, 5 times 2 is 5 times 1 plus 1, right? Which is 5 times 1 plus 5 times 1, which is 5 plus 5. And so that's why like multiplying by 2 is the same thing as adding something to itself twice. I'm adding one addition, but two numbers, right? So like that's kind of, so it actually comes from like, these are connected, I guess is my point. Like the distributive law and that idea are connected to each other. And the idea of multiplication being repeated addition, I don't know, maybe I should be opening this up to discussion more, but like, again, why is a times 0 equals 0? given that multiplication is repeated addition, I don't know, like what if I do kind of, I feel bad just like imposing all my thoughts on you.
The way I would explain it to a 5-year-old is like adding something to itself. If you don't do that, if you do it no times, you don't have anything in the first place.
You don't have anything. Yeah. Sorry, you're a little quiet there. But what you said, I think what you said is like, if you add, yeah, like a times 0 means adds a to itself no times, right? 0 means nothing. And if you add something to itself no times, you should get nothing. So I think that's a first great insight. Like that's what a times 0 equals 0 comes from, right? So like, so let me just write that down. So a times 0 means add a to itself no times. No times. Almost want to put like quotes inside quotes. No times. And so yeah, so it makes sense that. Sorry, no, Colin said, yeah, what Colin said makes sense. So it, so that's good. I mean, that's definitely a level. So we're kind of bringing the levels together. I gave you like the formal level, and now like there's some level down here of like just like what it kind of means. But there's still something there that's a little bit like we haven't quite connected the like high level perspective to the low level perspective, because like how do you, I mean, you could sort of again say like, okay, like yeah, distributive laws repeated addition, and but then what does that really, does really a times 0 mean add a to itself no times? Like again, intuitively, yes, but axiomatically, does that what it means? I guess one insight that I've had like over the years that makes it feel right to me, again, has to do with this idea of sets and maps. Like I said, everything in math, it's going to be a repeated theme of this course, is that everything in math is a set or a map between sets. You can actually think of multiplication as a map, as like a function from one set to another. Sorry, map and function are going to be interchangeable words, which will come up. Again, this is the first day, so I'm probably throwing lots of stuff at you. But there's another sense of what multiplication is. There's a geometric sense. What's the geometric sense of what multiplication does?
This is sort of a shot in the dark, but I've heard it explained as like stretching. Like
Does that seem right to people? Yeah, right. Like if you double every number, you're sort of stretching the number line out by a factor of 2, or you like, yeah, you multiply some block by 5, then you're just like stretching it out, or like, I don't know, a piece of clay or something. Like I want it 5 times as long, I'm going to stretch it out. Silly putty or something like that, right? So it's stretching or scaling. Like, so that's another thing. So like, you know, again, I'm just sort of writing stuff down about like, this is a little bit kind of, you know, all over the place maybe, but so let's just like keep going. It's almost like just going over stuff over and over again to give yourself more and more insights. And I'm almost giving you my path through it, and then trying to just to show you what it's like. But then to say that this is very quick, and it's like stuff you have to mull over and think about. So multiplication is scaling or stretching or shrinking. So scaling is the word people tend to use. And it's like, okay, if I have the number line, so let's think about this. I have the number line. This is a way to represent the integers, right? I don't know why I'm writing this many. Okay, and then let me do something here. Let me like use different colored dots for these. Hopefully it's going to be obvious enough that they're different colored. Just do -1 also, and maybe -2. Okay, and now if we think about, this is probably going to be 2. Okay, so let's think about multiplying everything by 3. Let's just pick a number to multiply by. Or we could say, let's say multiply by a. Actually, yeah, let's just use a. Okay, then basically, I want to draw the number line again. This is what I'm talking about as a function, like a function from the integers to itself. Like multiplication is a function. If we fix an integer and multiply everything by that integer, that can be considered a function, right? So this is a map, a function from z to z. Function slash map. Okay, well, so here's the thing. We can say where this ends up, right? We can say where this ends up. We can say where this ends up. Yeah, like this is at A, right? And what's the orange dot? What would I label the orange dot? If I multiply everything by A, then 2 goes to 2A, right? And this again is also capturing the repeated addition aspect of this, that it's like A plus A, you know. It's almost like, I kind of wish I had these actually stretched out even more because I'm sort of losing that a little bit here. I guess I could do that with notability. Oops, that's not what I wanted to do at all. No. I could stretch it out. So they're farther and farther apart. Oh my God. That was ridiculous. I'll make these smaller now. So A, 2A, 3A, 4A is over here. So we're taking these little distances, like, I need another color, like this distance is 1, and now it's stretched to A, right? And this distance is 1, and now it's stretched to A. And now tell me why A times 0 equals 0. Do you guys see it? Where does the purple dot have to land under this? You see what I'm getting at? Does anybody see what I'm getting at? Or am I being too obtuse? Certainly possible that I'm being too obtuse.
The purple dot have to be at 0 so that the distance between 0 and A is A.
Yeah, it's like, well, right, if we want to maintain the stretching aspect of the separation, then we have a gap of 1 right here, and it's going to a gap of A. And so you can just tell A has to land at 0. I mean, 0 has to land at 0 under this map. So, so this must be 0. And then it's like, okay, then you can almost see yourself going from this to like the proof that we wrote down, which is like, that's kind of what we're using, right? We're sort of stretching, we're stretching the gap between 0 and 1 to a gap between 0 and A. So it's like, that's why we're using the 1 plus 0 equals 1 back way up in the proof up here. Oops, right here. That's why we're using the 1 plus 0 equals 1 and then multiplying by A to stretch everything. And then showing that A times 0, using the distributive law, showing that A times 0 has to land at 0. So to me, that's like this proof isn't come out of nowhere. It's like it can be seen to come out of nowhere, which is again like can be a discouraging thing about mathematics, like that proofs often seem to come out of nowhere. And but there's always an insight behind it, you know, and it's what you want to, that's really what you want to try to find, is the insight behind it. It's still quite a process to turn that insight into this proof. I'm not going to say it's like an immediate thing, but by the way, on the first problem set, I'm going to ask you to prove that -1 times A is negative A. On P set 1, you'll prove, well, let me just write it, yeah. -1 times A is negative A. So that's the additive inverse of 1 multiplied by A is the additive inverse of A. But that's kind of in this picture also, right? In fact, that's why that's why I actually drew the negative sign, the negative side of this, was that like you also are going to have this gap of A, and you can sort of see where this is going to land. And so thinking about how to maybe formalize that into a proof is an interesting conundrum. What did I do over here? I completely covered up this Z right there, didn't I? Let me just write this again a little better. So that's Z to Z. My stretched version of the number line. So I'm saying use the same insights. Like you'll have to use the definition, but you might think about what equation you would start with. That's similar to 1 + 0 = 1, and try to build the same kind of argument, you know? Does that make sense? I don't want to say too much because you have to do it yourself. Okay, wow, I can talk. I can really talk. I've been talking for like 75 minutes straight now or more. So I apologize for that. I will try to break stuff up with like some group work and some stuff like that. But I wanted to give you some like first, like what is a proof and what are the insights kind of thing. I have a handout about like what the axioms are, like typed out version, which I'll post. Because there's also a couple more axioms that actually define the integers, and we'll talk about those later. I will say just in the last couple of minutes, last 5 minutes, we still have like 6 minutes left, but maybe just for 5 minutes, and I'll let you go. There are not so good proofs. And there are like proofs that students try to write at first, which is fine. You're going to go through a process of learning how to write this stuff. It's not going to be easy or obvious at first, but let's just think about another attempt at a proof. So what a lot of students will do is they'll start with what you're trying to prove and then reduce to something true, like 0 = 0 or something like that, you know? And there are issues. There are issues with that. There's a lot of issues with this. First off, it's kind of backwards because you shouldn't assume the thing you're trying to prove, right? Like, you know, start with this and then reduce to something that's true. That feels like an argument. And that's not necessarily inherently wrong. But the logic is backwards because you're supposed to end up at you're supposed to start from axiomatic things and end up at the statement that you want to prove, right? So that's already a problem, sort of like, don't start with what you're trying to prove. That's another thing we're going to talk about a lot in this class, are just all the pitfalls it's easy to fall into when trying to write proofs. But when you're just playing around and thinking about stuff, like, that's not necessarily a bad thing, right? Because now you could be like, well, like, you could imagine how to do this, right? You could say, like, maybe a better thing I would say is, like, say, but this shouldn't be your final proof, but when you're trying to like come up with an argument, when you're trying to, because you're not going to start with the first thing and end up with the proof. Like, that's something that I'm trying to make and not being explicit enough about, which is, like, you're not going to just write a proof from start to finish. Like, you want to mess around with the symbols, move things around, think about the insights, like, what does this mean? How do I connect these things? Like, all the stuff we're talking about. But see, I gave you the nice proof first. That's really the last step, is writing down the nice proof. You're going to want to mess with stuff. So you could start with, like, this with a question mark over it, which is like, is this true? And then you could say, well, I don't know, maybe I could add a to both sides. It's almost like a backwards version of the proof we did, actually, but it's something that you could imagine doing. And now you have, like, a times 1. You could then do the you could imagine doing something like that and then pulling the a out. I mean, maybe this is just as like random to you, but, like, this actually almost is closer to the argument, that the geometric argument above, which is like, it's almost like I don't want to put, or I could also just put like a question mark here or something, I don't know. But it's like the fact that we're adding, when we add a to a times 0, it should be the scaled version of this. So it's like actually almost connected to that. And then it's like, well, then that would be a times 1 equals a, and that would be a equals a, and that feels right, right? So these are like question marks up into this point, but then that's actually not a question mark anymore. It's just like true. You see what I'm getting at? And there's nothing wrong with, like, doing that in part as part of the process. I mean, it's an important part of the process. Like, just start playing around with things and seeing if you can manipulate stuff. Like, again, if you have the insight about the distributive law, you realize it's going to come into play somehow. So I need to get something involved. And a times 0 is too abstract without, you want to, like, move things around. The problem is you have to check, can I actually reverse all these steps? So this is still backwards. Oh, geez, we're gonna have time, are we? Still backwards, but if all the steps are reversible, but are all steps reversible? Here, yes, you can actually check that, like, you could actually justify all these, right, axiomatically. And here, this is a couple of steps, this last. And so you could do a proof. This is another proof, actually, just if you reverse all the steps of this and give justifications for them, right? Like, you could start with a equals a, then you could do a times, you could rewrite the left side as a times 1, right? The left side is a times 1 plus 0, distribute, and then cancel the a, add negative a to both sides, I guess, to get that, So that's another proof. So that this leads to another proof. It's a different proof from the one I wrote down. I mean, it's sort of the same proof, actually, but I'll just say that like, there's lots of different proofs, and you want to sort of try to work out the logic. Sorry, this is another proof. Oh man, I just realized I'm a minute over. Okay, I'm sorry. Okay, so that's a good first start. We'll dive into logic on Thursday, so you might start looking at chapter 1. I'll try to post on the class meeting 2 page, maybe some like stuff like more specific reading, but I would start looking at chapter 1 just to start diving in to this stuff, and then I'll post the problem set like very soon also. So, all right, everyone, thank you. Sorry for keeping you a minute over, but welcome to the class.
Thank you, Professor.
Thank you.
Thank you.
Hey, so I have heard through the grapevine that when it comes to the Putnam competition, you're the man. You're the man.
Oh wait, let me stop the recording. This doesn't need to be part of the recording.